Hello everybody, Mr. Chandler here to go over graph linearization with you. Graph linearization is an important process in AP Physics 1 where we take some curved graph of any kind of curve really, and we can manipulate the data in such a way that we kind of turn it into a straight line graph, which is useful for us as we'll see today, because then we can find the slope, and the slope can tell some very useful and important information. So let's get started, and I'm going to walk you through a couple examples and then use some data that we got from class today and then show you how to linearize it and then take the slope and do something with it that's useful that we want to find. So let's get started. There we go. All right. So first we're going to start off talking to you just real quick. I'm going to recap about the types of relationships we have in physics. Now, there are more than I'm going to show you right now, but these are the basic ones, right? And I went over these briefly today in class, but just to highlight it again for the video, we got a basic graph here, y-axis, x-axis, and the first kind of relationship we have is a linear, or otherwise sometimes we call it a direct relationship, right? This direct relationship, it can be written some certain ways, like we can say y is proportional to x. What that means, remember, is that if we were to do something to the x value, if we had like a data table, right, some x value, y value, and we had, numbers here or whatever, I don't know, just gonna make up some numbers here just to prove a point. And we say, okay, well, if I double my x value from 2 to 4, right? I times it by 2. If I times this value by 2, the corresponding y value, if I'm gonna go, if I double the x value, I should also double the y value. And sure enough, I do. 16 to 32. I doubled one, I doubled the other one, right? I multiply them both by 2, and I can make predictions into the future that way, or into the past that way. With a direct relationship. They're directly related to each other. Whatever I do to one variable, I do to the other one. That's called a direct or linear relationship. We can also, or I want to remind you rather, that you can also know two objects are related this way if you get the b value to be equal to 1 when you do a power regression on your calculator. If your b value is a 1, then that means that it is a direct or linear relationship. We can also have a relationship that looks like this, a graph that looks like this. This is called an inverse relationship, and this is going to be y proportional to 1 over x, and the b value of this one is a negative 1, right? We can also have graphs that look like this, they curve up. This is going to be exponential, or sometimes called quadratic, or sometimes called just a squared relationship. This is y proportional to x squared. And then the last one I'm going to talk about right now is going to be this guy. This is a root relationship. And this is y proportional to the square root of x. And the b value for these, the b value up here I've got to give you, this is going to be 2 for this one. And the b value for a root relationship is negative. I'm sorry, that's not right. It's 0.5 or half. All right. So depending on the kind of relationship we have, this will matter when we go to try to find out how to linearize a graph. We have to first find out, okay, what is the relationship between my two variables on my curve? What kind of curve do I have? An exponential curve? Is it a root curve? Is it an inverse curve? Once we know the kind of curve we have, what the relationship is between the variables, we can then take the next step into linearizing the graph. Let's do an example, and I think it'll make more sense. So here we have some data, period and frequency, right? Straight, very common variables to measure when we're talking about a certain kind of relationship. I won't say what it is yet. So if I were to plot this data, I'm going to pop over to Excel real fast. If I were to graph this data, all right, here is my period and frequency. If I were to take this data and plot it, and I did this in class, but I want to go over it again, that way you can watch it over and over again, and insert a chart, scatter plot. You see, this is clearly not linear. You can just tell by looking at it. If I were to plot a linear graph here, linear trend line, that's not a very good fit to the data. So I don't think that's right. So then I gotta ask myself, well, what kind of relationship is this? What is it? How are these two variables related to each other? To do that, I want to get out my calculator, and I'm sure there's a way to do this in Excel, but I'm not sure what it is. So whatever. Go to Stat, Edit, and I'm going to put in these numbers here. Clear this old list out. put in my new list. So 0.946. Oh, not negative. 0.946. All right, and then I got 0.45. I gotta do this fast. 0.2493. 0.1072. Feel free to skip ahead to the next part. 0.0571. 2.222, 4.01, and 9.3. Okay, there's my values in there. And then I'm going to go to stat again. Arrow to the right to go calc. Arrow up to power regression. Hit enter. Scroll down to calculate. Hit enter. Let it think, and it's going to spit out a number. Negative 0.998. That's really close to -1, isn't it? I mean, that's super close. So go back to our list here and say, okay, well, looks like inverse is the relationship we got here. It's almost exactly -1. You never get exactly the number you're looking for, but you can hopefully get pretty close. So -1 means inverse. So back to Excel. All right. So now I know this is an inverse relationship, right? The reason why it's not linear is because these variables don't have that kind of relationship. They don't have a proportional or a direct relationship. These two variables are inversely related to each other. But we can force them, we can manipulate them into being linear if we take advantage of our knowledge of the fact that, hey, these guys have a linear relationship. So instead of graphing frequency and period, frequency here, and period down here, what if I graphed, instead of graphing period, and the period here is like my x value, right? It's like the x-axis. Instead of graphing period, what if I graphed this instead? Because y is proportional to 1 over x. In this case, let's rewrite this just so it's I want to be very clear about this. We're saying frequency is proportional to 1 over period. But we graphed, what we graphed was frequency into period, right? That's what we graphed. That's why we're getting this curve. But if we were to graph instead 1 over the period, our graph would turn into a straight line, right? Because we would then force it into this linear relationship. Now, as it stands, we got this curve. But we didn't graph this, did we? We just graphed period, all right? So let me show you what happens. Now, real quick, just some Excel fun stuff. I'm going to go to my trend line, and I'm going to make this a... Is there an option for inverse? I don't know if there's an option for inverse. Maybe there is. Let me see. I don't see an inverse trend line on here. That's too bad. What a bummer. Polynomial order -1. I don't know if I can make it a neg... that's not very good either. I don't know. Oh, that's pretty good. Power. I'm not sure what a power... it doesn't matter. It's just too bad. We can't make it a inverse trend line. If we could, we'd see... You can kind of tell... Can I draw? I can't draw in Excel. Cool. You can kind of tell by looking at the picture here that this is kind of making this shape, right? The same general shape that we had on this graph here, okay? That curving down like that. All right. So now what I'm going to do, I'm going to take the period, right? And I'm going to force it to be 1 over the period, right? I'm going to graph 1 over the period. So how do I do that? All right. I'm going to do inverse period here in my Excel, just to label that. And I'm going to hit equal sign. I'm telling Excel, hey, I'm going to give you a formula to do. I'm going to do 1 divided by, and I'm going to click on the period cell, A2, hit enter, and it takes the inverse for me. Then I'm going to grab that little green dot at the bottom right, that little green square. I'm going to grab it and drag it down, and it's going to fill in the rest of the blanks for me. I'm going to move this chart out of the way just for a second. And now I'm going to graph these two variables, all right? And I'm going to copy this over to here because Excel likes to have Excel really likes to have the x-axis be the first thing you grab. So whenever you highlight these cells, the x-axis is always going to be in the left-hand column. You can change that, but it's a pain in the butt. I don't want to bother. So inverse period now on my x-axis, frequency on my y-axis. Insert a chart, scatter plot, and look at that. Look how straight. Insert a linear trend line, and boy, that just lines up beautifully, doesn't it? Now we know, oh, Okay, there we go. I can find the slope of this line. I go to Excel. You can do it in, on paper too, but Excel's got lots of nice features. I right-click on the line. I go to Format Trend Line. Over here you see where it says Display Equation on Chart. I click that, and there's my slope. It's almost exactly 1. It gives you the equation of the line in y equals mx plus b format. So the m, right, the number right here, the 0.996, that is my slope, right? That's the m variable, the slope of this straight line. And then my y-intercept is 0.0077. Okay, so there we go. That's how we can do that. Okay, and all right, cool. So that's one example of a linearizing a graph. Let's do another example. Go back to my PowerPoint real fast. So in this next example, I'm going to give you. So let's just go to Excel. I don't think we need the PowerPoint. In the next example, I'm going to use data from my 7th period class today. They got really good measurements when they did their lab. So here is what they got for time, and these are the heights we dropped the balls from, right? 1 meter, 1.5, 2, so on. These are the average of their times. If we take this information as data and we insert a chart, scatter plot, we get this. Now, if I put a linear trend line on here, it looks like this. And I talked about this in some classes. Let me mention it again. If I kind of extend this line down, right? If I kind of imagine this line extended further down, it would intercept the y-axis about 0.3. We know that this cannot be the correct trend, the correct type of relationship, because what this implies is that if our height was 0, we dropped the ball from a 0 height, in other words, it's already on the ground, that the time that would take would be about 0.3 seconds. But that makes no sense, right? If the ball is already on the ground, it doesn't take any time for it to fall because it's already on the ground, right? So we have to recognize that, hey, you know what? This graph should go somewhere close to the origin, right? Because if your height is 0, your time should be 0. So it might not hit exactly on the origin, but we should get some kind of graph that goes pretty close, right? So what kind of relationship do these variables have? All right, well, let's find out. Let's go back to the calculator. And I think we did this in most of the periods today, but let's do it again because I know I messed up in 2nd period this morning. So edit my list. And let's get those numbers in here. So we're going to go up here and we're going to clear out this list. And we're going to go up here and we're going to clear out this list. And here we go. Time is 0.4306, 0.5352, 0.6672, 0.686, and 0.746. And then L2 is my y-axis. It's going to be 1 meter, 1.5 meters, 2 meters, 2.5 meters, and 3 meters. All right, now I'm going to go to stat again, calc, edit over to power regression, go down to my calculate, hit enter, and I get 1.9. Boy, that's a really good relationship. That's very good measurements by my 7th period class. So props to y'all. You got good measurements. You did a good job. 1.9 is awfully close to 2, isn't it? And remember 2, go back up to here, 2 was exponential or quadratic. And I believe I misspoke during 2nd period today and said it was, I don't know why I said root, but it's not root, it's quadratic. It's exponential. It's an x squared relationship. So now we know that. We come back and say, okay, well, on this graph here, I can get a better fit to my curve if I change that trend line to be quadratic, which there is an option for that one, or exponential, same thing. And look how nice that fits. And if we imagine this curve going down here like this, we can kind of tell that if it keeps curving, it's going to go pretty doggone close to the origin, isn't it? It's going to almost hit it exactly. That's a sign that you got the right relationship in this case. All right, so let's go ahead and find and linearize this graph. So now that we know the relationship for this is going to be y proportional to x squared. So remember, we didn't graph that, right? We didn't, remember, instead of, let's replace the y and x's with actual. So remember, y is the height, right? How high we were. Height is proportional to time squared. But we didn't graph time squared. We graphed just time and height, or position, whatever. Well, what if we graph time, and when we graph this, we got this curve, right? But what if we graph time squared instead? What if we put a square down here and we graph that? We should get a straight line because these two variables are proportional. right? These two are. We didn't graph them, though. We graphed that, and we got the curve. So let's graph time squared instead. So go back to Excel, make a new column here. I'm going to call this column time squared, and I'm going to put in my equal sign here. Tell Excel, hey, I'm getting ready to give you some formula. I'm going to put in this number, and then I'm going to do caret, right, to the power of 2, enter. There, it squared it for me. I'm going to drag this down, and I'm going to populate the rest of that list. And then over here, I'm going to put height again. Remember, that's going to be my y variable. I'm going to put these numbers in there. Nice and easy. Okay. So now I'm going to graph this information. So now this is time squared on the x-axis and the y and the heights. Let's see what we get. Let me graph this. Insert a chart, a scatter plot. We got one outlier right here, this little dot here. But other than that, you can tell if you can ignore that one outlier, man, that looks like a straight line. In fact, we go to add in the line, trend line, linear. Yep, that's a pretty doggone straight line. And if you look down here, you kind of extend this line down, you can tell that, yeah, it might not go exactly through the origin, but man, it's pretty close. It's really close. So that's a really good line there. So if you're going to use Excel to print these, remember you want to change your chart title. Chart title, not a good chart title. So this is our free fall, graph, or height versus time is good too, whatever. You want to add in your axis titles. This is height, or you can say position, either way, same thing, in meters. And this down here is going to be time, in seconds, of course. And then we want to add our trend line. This one's going to be linear. This one will be curved. You're going to turn in both these graphs to me, either by hand or on Excel. I don't care which one. You can print it out on your own. Let's focus on this graph for a minute, though. I'm going to add in this. I'm going to right-click on here and go to Format Trend Line and add in the equation. And there it gives me the slope. So the slope is 5.557. All right, so let's write that down. Let's just go with 5.16. Back to my PowerPoint. All right, so my slope here, we found the slope. We graphed height, displacement, right? Change the position of height, it's displacement, times time squared. A straight line whose slope was 5.1. What did I say? 5.1 what? 6. 5.16. Now, I want you to look at the units here, right? Or not the units, but remember, what is slope? Rise over the run, right? So the slope is the rise, the change in position, right, from down here up to here, divided by t squared, right? The change in my t squared values, right? The x-axis. Now, I want you to think back. We have this equation that we haven't used a lot yet, but we will very soon, from our kinematics. It's the second formula on your formula charts that you'll have. The equation looks like this. It's delta x equals 1/2 at squared. Now, the whole point of this lab, right, was to find g, the acceleration due to gravity on Earth, right? So g is a value of acceleration. That's what it is, right? We just call it g. It's a special value of acceleration because that's how much acceleration we get on the Earth, right? Like things fall with that acceleration down, right? You go to the moon, it's different. You go to Mars, it's different. But on Earth, it's special, so it gets its own letter. It's a little g. I'm going to replace this a with a g because that's the acceleration that we're going to find, right? Remember, g is an acceleration. I want to rearrange my equation for g. Okay, let's do that real quick. So I'm going to times 2 both sides, times 2 here, times 2 here. They cancel to half. Half and the 2 cancel. So now I have 2 times delta x equals gt squared. I'm going to divide by t squared. So these cancel. Now I'll go over here. Now I got 2 delta x over t squared equals g. Now I want you to look at this. Look at this right here. Look at this. What was our slope? Right. Isn't the slope rise divided by the run, the y-axis value divided by the x-axis value? That is the slope, right? That is the slope. You see that? So what I can do is say, well, since now I have a straight line, the slope is constant, right? Straight line. Slope never changes. The slope in this graph is always 5.16. So I'm going to, instead of writing delta x over t squared, I'm going to replace this term here with my slope value, which is 5.16. So now I'm going to write 2 times 5.16 equals g, right? I replace this with this number because this value is this variable, right? This is what the slope is, rise over run. So I replaced it. And what do we get? We get g equals 10.32, which is pretty doggone close to 9.8, right? I mean, that's really close. That's a very good measurement by 7th period. If you got 9.8 exactly, I would be astounded, but this is really good measurements. Okay, we got really close. So this is what you're going to be doing in your lab reports. You are going to take your data from just your group, right? You're going to linearize your graph. You're going to find the slope of the linearized graph, and you're going to rearrange this equation to get this guy, and you're going to replace this section here with whatever your slope is times 2, and then you get the slope, or you get the acceleration of gravity, the acceleration due to gravity on the Earth, right? And that is graph linearization, and that's how it's useful. We can even take a curved line and change it up, manipulate it so that it can give us useful information. Okay. All right. That is it for me today. Hopefully that was good. Rewatch as much as you need. Ask me questions, email, remind anytime. If something isn't clear, I'll see you guys in class tomorrow. Bye-bye.